Now you guys are recorded, so same thing. Oh, I should have started the icebreaker, but that's okay. You guys can start off with your type your answer to me. And then we can solve it in like okay, thanks. Bye. I'm unmuted. Yay! I think a lot of people got the answer. I think this was actually an Amy question. I give you guys an Amy question. AMC, it was interesting. It was like an early AMC question. Yeah, it was like number one. I think it was number one.
Oh, yeah.
So for people who are saying like this is like math counts, this is Amy. AIME. And I know a lot of you guys want to make it. Okay, Timothy, go to.
Okay.
Okay. Timothy is so annoying. Oh, yeah, this is. Okay, so I think Missy got it. And I think I can just write now. Okay. So let's go back to me. So the question is, can't see, it's 3 this 3 over 3 factorial. So we can just kind of solve for this one. So you can just do 3 factorial is 6, and then kind of solve from the inside out. So this, and then you get like 720 factorial over 3 factorial, which is like so if we want n to be as large as possible, and then we're supposed to write this in the form of k times n factorial, and we want n to be as big as possible, we know that 720 factorial is equal to 720 times 719 times 718 all the way to 1. So we can actually rewrite it as 720 times 719 factorial all over 3 factorial. And so then this, so this would be, and then you can actually, since 720 is divisible by 3 factorial, which is 6, we can just write that here. We get that 120 times 719 factorial. And when you add it up, it's 839. So that's what you guys should have gotten. Yay! Amy question first thing. Woo! Okay, so now we're gonna go through today. I'm going to give an overview of what we're going to learn first. So first, I'm just going to tell you basically what you're going to be slightly expected to learn, some review stuff that I think most of you should know, aka like divisibility, units, digits. Yeah. And then we're going to go into actually what we're going to learn today, which is, I believe, Euclidean algorithm. And there's going to be substitution involved. There's a type of substitution used in Euclidean that helps you solve for Diophantine equations. And if you don't know what I'm talking about, that's okay, because you'll learn. And then we're going to go to Bézut's lemma and like Euler's. We're going to just look at Euler's-Tauschent theorem, Wilson's theorem, and that. And if you still don't know what I'm talking about, that's okay, because we're gonna do it today. So let's go back. So today, we're gonna first review divisibility. For AMC 10, make sure you know the divisibility rules for 2, 3, 4, 5, 6, 8, 9, 10, 11. So know that 7 is not one of them. You can just divide for 7. I don't think you need to know the one for 7. 11 is actually really important for, even though it seems like one of those that isn't that important, it's actually quite useful in that, that because basically what you do is you add and subtract alternating digits. And if you don't know, you can search it up, but make sure you know that. So one of these, you can do the practice problem if you would like, but it's really easy and it's from our state, so I put it down there. And so basically, this is what you'll be expected to know. This will be on like number 1 through number 10 on ABC 10. Nowadays, since it's gotten so much harder, it's probably number 1 through number 5. You're not going to see much of like divisibility rules early. Okay, so prime factorization. So make sure you know how to find the prime factorization. Yay! Okay, now we're gonna go. So make sure you know the number and sum of divisors, just some simple stuff like that. And it just looks complicated, but you guys probably know how to do it, right? Give a thumbs up if you know. Oh yeah, sum is like kind of easily forgotten. Okay, sum. So sum, let's say 12. How do you find the sum of divisors? Well, you can add it up, obviously. And if it's small enough, like 12, it's probably easier if you just add it up individually. But another way is you first factor it. So you get, okay, 2 squared times 3, right? Now you take each distinct prime divisor and I'm sick. And so you can just do 3 plus 1 or 3 to the, this is bad. Okay. 3 plus 3 to the power of 0, 3 to the power of 1 times 3 to the power of 0 times 2 squared plus 2 to the power of 1 plus 2 to the power of 0. Right. So notice how all the factors can be generated like this. So 12, 6, 3, and so on. So that's why this works. I think this is tau function. But basically, this is the easier way to calculate it because then you can calculate 4 times 7, which is 28. And I think that's right. So that's how you calculate the sum. And what I wrote there was basically the sum of the primes. Let's see. Does anyone not know? Oh no. If you guys find it too hard, just tell me. I'll try to make it slower. So I wasn't sure how much you guys knew, so I just kind of made it a little hard. So wait, do you guys want to practice? So let's practice. So what is the sum of the prime divisors of 45? And you can try to write it out like this. And so you would just do it like 7 to the power of 1. Like do the thing. Type it in the chat for me. For the prime sum of divisors for 45. Okay. Yeah, this is gonna be really quick. So yeah, most of you guys got it right. So it was 78. How would you get that? So 45, you factor it, equals 5 times 3 squared is 45. Now, we're going to, for each individual, oh no, I didn't say the sum of the sum of the powers of prime divisors. Okay. Okay, so basically you would find the power. So 3 squared. If the power is a 2, then you would sum up all of the powers of 3 that are less than 3 squared, including 3 to the power of 0. Make sure you don't forget that. And the same thing for 5. So it's 5 to the power of 1. So you would sum all of the prime divisors that oh oops, it cut off, but some of the divisors where that are less than or equal to it. So times 5 to the power of 1 plus 5 to the power of 0. And that will be 13 times 6, which is 78. If you guys need more practice, you can, yeah. Oh, I feel bad. This might be a little hard. This might be really hard. Okay, so we're just gonna skip that. And then the next thing, oh yeah, this is just powers of, and make sure you guys know how to find the unit digits too. So this is also like, it looks really hard, but you guys know how to do it, right? I'm questioning. So it's, I think this is very similar. So unit digit, you guys want to find this really quickly, what the unit digit of 77 to the power of 47 is. If you don't know, you can try to find patterns. Yay. Okay, so I think a lot of people got it. The answer was 3. So how you would do it? How you would do it is basically you unit digit, so you would like kind of test it out. So the really you can write it as 77, you can write it as like 70 plus 7 to the power of 47. And then you realize that the 70 doesn't actually affect the units digit, only the 7 does. So it's really asking for this. And then you kind of just test it out. So 7, 49, so last digit is 9. And then when you multiply again, 343, last digit is 3. And then I think it's like 2401, something like that. But the last digit should still be, should be a 1. And then it just repeats 7, 9, 3, 1. It repeats every 4. So then, so when you try 47, that's 3 mod 4. So you would take the third remainder, and that would be 3. The answer is 3. Okay. Yay. That's not that bad. Okay, modular arithmetic. So when I gave out that Google form, most of you said that you knew how to do these operations. So I just did it really quickly. So basically, what addition is just saying if we add the same thing to both sides that are already equal, then it's the same thing. So we can just add the same thing to both sides. Same thing with multiplication. You can just multiply the same thing to both sides. Oh, I'm gonna give you guys these handouts. So a lot of this notation is kind of weird, but this upside down A means for all. So for all AB, all like random numbers in integer set, the in integer set, you can set this equal to. So see, the notation is hard, but you know what it means. It's basically just multiplying. And then division. Division is hard. So division, you guys might not know this one yet. But basically, when you divide both sides, you can't just leave it, the mod 16, the same. Like for multiplication, we didn't do anything with the mod 5, and it stays the same. But for division, you have to divide by the mod by 2 too. Otherwise, you can't divide it. So let's say if this is, yeah, otherwise you can't divide it. So if this is like, for example, if you were given something like 16 is equivalent to 4 mod 3 or something. 4 mod 3. You can't just divide both sides by 4. That's just not allowed, unfortunately, because otherwise we would have a fraction. But anyway, that's basically you can't, you have to divide by whatever the mod whatever is divisible by. So that's how division works. So here 6 is equal to 2 mod 16. If you want to divide by 2, you can, because 16 is divisible by 2. So when you divide both sides, you get 3 is equivalent to 11 mod 8. You guys have any trouble? You can just text me. It's very, oh, So, okay. So then the Euclidean algorithm. So Euclidean algorithm, I'm just not going to scare you guys with the notation. What the so what let me help someone quickly. What Euclidean algorithm is saying. So let's say there's two numbers. Let's say it's like 8 and 4. Okay. What Euclidean algorithm is saying is if a number is 8 is divisible by a number and 4 is divisible by a number, then 8 minus 4 equals 4 will also be divisible by whatever number they are both divisible by. So in this example, 2 is divisible by 8, right? And 4 is also divisible by 2. 4 is also divisible by 2. And Euclidean algorithm just tells us, okay, that means 2 is also divisible by 4, which isn't a good example, but let's say 12 and 8 right here, right? So 4 is divisible by 12. Oh, 12 is divisible by 4. 8 is also divisible by 4. So their difference is also going to be divisible by 4. That's what it says. Now, what an interesting thing we can do with that is we can find the greatest common divisor. And you guys know what a greatest common divisor is, right? Greatest common factor divisor doesn't really matter. So let's say, oh, this is hard. I forgot. Okay, so let's say there is like 24 and 16. Not 16. Let's see an inch. Let's do 8, right? So what Euclidean algorithm tells us is that 24 minus 18 is divisible by the greatest common divisor, because the greatest common divisor is 24 is divisible by their greatest common divisor, and so is 8. So this is 18. Why is this 18? 16 is also divisible by the greatest common divisor. So then we're getting 8 and 16. We need to find the greatest common divisor of 8 and 16 because the GCD of this is also equal to the GCD of 8 and 16. So that means we're just trying to find the greatest common divisor of 8 and 16. And then from there, we also realize that the greatest common divisor of 8 and 16 is 8 and 8. And that is obviously 8. So then you just get the greatest common divisor. Okay, I want you guys to try it with like bigger numbers. So like 427 and, oh wait, no, that's too big. Let's do it with 54 and 16. Try using the Euclidean algorithm to find the greatest common divisor. Okay, and the thing with Euclidean algorithm is that it's easy with it's okay. I mean, why would you do Euclidean algorithm with these two numbers when you can just prime factorize it, you know? So So 54 and 16. Yeah, why would you? So Euclidean algorithm is best when the numbers are super, super big. So if I gave you like in the thousands, like that's what like AIMC tends to give you. They're not going to give you easy numbers like 54 and 16. They're going to give you like 1,243, something like that. But it's easier when you have two equally big numbers, because then it's super hard to factor it. Yeah, Brandon got it right. Oh yeah. Okay, so I'm gonna explain it because I'm gonna explain it now because this is because we have a lot. We have to do our study group thing too. So okay, so let's go to okay, so a lot of you found a shortcut for this would actually be so you would get 5416, right? And then you get like 3816. And then you get this is all greatest common divisor. I just got lazy. And then that is equal to 22 and 16. Why am I struggling? 22 and 16. And then you keep getting 6 and 16. And then 6 and 10. You subtract from the bigger number, by the way. I mean, you can subtract from the smaller number, but you'll get negative. And then you end up getting 2, 2. But one easier way is obviously you can just subtract like a huge chunk of 16. So you can just subtract like to skip all these steps. You can instead just do 54 minus 16 times 3. Basically, you're subtracting 16 3 times. But, and then from there you go, oh, 6, 16. And then you subtract 6 twice from 16. And you just immediately get to 6, 4. It's a lot faster. Okay, so I should give you guys some practice. The example I gave in the handout, it's a lot bigger, but it's basically the same thing, except I moved everything over. So instead of 190, so the greatest common divisor of 141 and 193 is equal to 52 and 193. Oh, and 52 and 41, and then it's 37 and 52, and then 15 and 37, and then 7 and 15. Basically, what you get is equal to 1. And this is the way you would solve for this is like we're applying Euclidean algorithm multiple times. So what you're doing is you're finding the greatest multiple of 141 less than 193, and then you're trying to find the remainder. This is the remainder. And you can, last time I wrote it in like subtraction form. I wrote it in like addition form. It doesn't really matter. You can move this over and it would be 193 minus 141 is 52. That's probably the form you guys are most comfortable with. And then you just keep going and you keep track of your remainders because the Euclidean algorithm basically says that this 1 is the greatest common divisor, greatest common factor. So basically I already said this. It's only helpful. You guys want to do bigger numbers. So this is basically what AMC 10 will probably give you. You guys can try this. Euclidean. Oh, I think I'm moving really fast, but 1008 and 932. And yeah, you guys want to find that. Okay, so what if the vice president wanted to give this question to you guys? Wait, after you guys have done this one. After you guys have done this one, but he wants to give you this question from IMO, if you guys want to try it. And it's like you could do it using Euclidean algorithm. If you want to try. You guys want to try. I actually I can just show it on here for if you guys have solved it. Yeah, just really easy. Like it's simple IMO. Okay. So here, you guys, oh wait, no, I can't. Right there. If you guys want to prove it. I will. Okay. If you guys want to do that. By the way, the correct answer I think was 4 for this question. Yeah, I think it's 4. So I can do it really quickly. All right, I'm moving really quickly because like we were supposed to give 1 hour for the study. Okay, so 1008. Let's do 1008 and 932. So let's write it in the form I wrote it. So 932. What would be the remainder be when we divide 1008 by 932? Oh well, and what's the quotient? Well, the quotient is 1, if you can tell. And then the sum, the remainder would be 76. And you go 932 equals 76 times, what is this equal to? 932 divided by 76 is 12. So it'd be 12. And then I don't have paper with me at the moment. Okay, it's 20 plus 20. And then keep going. And then 76 equals 20. What's the quotient? 3 plus 12. Oh, 6. What am I doing? 16. And then 20 equals 16 times 1 plus 4. And then you get 16 equals 4 times 4 plus 0. So the last non-zero one would be 4. Where's the answer? So basically you just divide it and then you find the remainder, you find the quotient. You don't really need to keep track of the quotient as long as you keep track of the remainder. You just look at the remainders. Okay, you guys want me to solve the IMO question really quickly? So it was, did anyone get it? Yeah, someone actually got it. Wow. Okay, so basically what you do, what you're trying to prove is that 21n plus 4 is irreducible. Do you guys know what that means? So irreducible means basically we can't simplify it further. So 7 over 4 will be irreducible, but 6 over 3 is not irreducible. 6 over 4 is also not irreducible. So we can keep going. So let's find what the greatest common divisor of these two numbers. Euclidean algorithm also works with algebra. So let's do what we did earlier. So 21n plus 4 equals 14n plus 3. Oh no, I'm running out of room. Times 1. It's times 1. Okay. Plus 7n plus 1. Okay. Now we go with 14n plus 3. You take the small number equals 7n plus 1. And you realize that this is this you can multiply by 2, and then the quotient would be 1, right? And so then you would get this. And then 7n plus 1 is the last set, is equal to 1 times 7n plus 1, which is obvious. And plus 0, so last non-zero is 1. So it says the greatest common divisor is 1. That means we can't divide both sides by anything. So wow, now you can tell your parents you solved an IMO question. Yay. Yeah, so actually multiple people got it. Okay, so that looks good. Now we're gonna go to Diophantine equations and Bezout's lemma. So why do we need to learn the Euclidean algorithm first? Because that's what you need to solve for Diophantine equations and Bezout's lemma. And we are not going to prove Bezout. So basically what it says is it gives this. Ax plus by given states that there exists x and y such that ax plus by equals GCT of a and b. Basically that's what that thing is. Let's say that you have 3x plus 4y. Basically, it says that we can always manipulate x and y so that this equation can equal GCD of 3 and 4, which is 1. Yay. And basically you can test, guess, and check, and you get like -1, 1 is a solution. Now let's like logic it out. Like why? Okay, it's easy to prove. Well, it's actually not easy to prove, but like, so like with 4x plus 6y, what is the smallest positive integer that this equation can be by Bezout's lemma? Oh, basically it says Bezout's lemma says that the GC. Yeah, so the answer would be 2, because the GCD of 4 and 6 is 2. Now, why can't this equal like 1? Oh, by the way, x and y are integers. They can't be like fractions. They can be negatives, but they can't be fractions. Like, why can't it be 1? Yeah, so Brandon brought up a good point. Is Bezout the same as extended Euclidean algorithm? It is, which is why you can use it. Bezout's lemma, it also looks a lot like Diophantine equation. So what is a Diophantine equation? So look at it. Diophantine. This is, oh shoot, why am Diophantine, can't write today, equation. Have you ever seen like a question where it asks you, find the solutions to 5x plus 6y equals 4? Something like that. That is what a Diophantine equation is, and look, it looks very similar to this. Yeah, okay. So that's Bezout's lemma. Now that I did say it was over the integer. I added it on later. Okay, so yeah. Okay. So it seems really easy, but it's actually been in the AMC question. Like this is number 22, but also it was like 4 years ago. So let's see. Okay, see it. So let's see if you. Oh no, it's like just happens to squeeze over. Basically, it's asked what is the smallest possible debt you can get. Oh no. Okay, I will shrink. Oh. You guys want to solve this? The wording is kind of confusing though. So it might take a while to get over the confusion, but so long to read. Bezout feels like a really simple lemma, but yeah. Okay, so I think a couple people got it. It was, the answer is 30 because basically what it's asking is, so pigs are worth $300, goats are worth 210, pigs and goats. It just sounds really confusing, but it says it's basically like 300 pigs plus 210 goats. Like, what is the smallest possible integer you could get this into? Because you're technically like adding and subtracting pigs or goats, depending on how low it is. Okay, so by Bayes' lemma, we see that this is equal to the greatest common divisor of 300, 210. Wow, a lot of you guys got it really quickly. It's number 22. So normally it's supposed to take a little longer. 210, and this equals 30. That's right, 30. Yay. Do you guys know why it can't be less than 30? Because both sides are, if like, notice how like we can go like 30, 10p plus 7g equals, what is the lowest possible? The ending has to be divisible by 30, and this is positive. So we're trying to go for a positive value. Earlier it said, what is this amount of the smallest positive? So we want a positive value. That means the answer, whatever it equals, has to be divisible by 30. So the smallest possible is 30. Smallest possible multiple of 30 is 30. Okay. We might go a little over time, but we have a lot of questions. And we're going to split you guys into groups after this. So I have to go through a lot because I'm going through like all of number theory. This study group is going to be 14 weeks. So we don't have a lot of time to cover a lot of material, but I'll try. So we're going to keep going. Forwards and backwards substitution. There's two different types of substitution. They're basically the same thing. And I will only teach you forwards. It's the same thing. It's literally like which direction you plan on going. And there's not an easier way or a harder way. Okay, so I think I'm gonna show it like this because it's easier to explain with an example. So how does forwards and backwards substitution work? So let's start with our earlier example of 54 and 12. And I think we figured out that the remainder is 2. So let's first write out. So this is what Brandon said earlier. Like, isn't it just expanded? So we're going to first write out Euclidean algorithm. So it's like this. You guys kind of like the quotient 54 divided by 12. The quotient is 4. And then the remainder is 6. 12, 6. Oh, wait, shoot, I messed up. 48. Oh, wait. Oh, I did with, what am I doing? 6. Oh, shoot. Wait. I'm screwing up. So 54. So it would then be 6 and, oh, wait, no, we did a different example. This is not the right example, but it's okay. We can do a different one. So then we get 6 times 2 plus 0. So the greatest common divisor is 6. Okay, we have a shorter example. So basically, we're trying to figure out what the solution to 54x plus 12y, when is this ever going to equal the greatest common divisor, which happens to be 6? And this example is really short, but wait, let me give you a different example. That's my bad. Let's do 54 and 8. 54 and 8. That was kind of obvious, but 54 and 8. So we get 54 equals 8 times smallest of 6. 8 equals 6. 1 plus 2, 6 equals 2 times 3 plus 0. So this is the greatest common divisor is 2. Yay, so we're trying to figure out when 54x plus 8y is ever going to equal 2. Okay. And then when is it ever going to equal 2? And basically what you do is forward substitution, it works like this way. So forward, we can, yes, someone already gave the solution to this. This is a way that you can solve without guessing and checking, because you can also guess and check. That's a little hard. So 54, you could say, actually, I might, backward substitution is a lot more intuitive. So I will show you backwards, and then I will show you forwards in the handout. Backwards, what it's saying is, okay, so we start with, okay, 2 equals 8 minus 6 times 1, right? And then if we go from the first equation, which is this, 54 equals 8 times 6 plus 6, we know that 54 minus 8 times 6 equals 6 times equals 6. So we can just plug in what 6 is equal to. So 2 equals 8 minus 54 minus 8 times 6. Oh, I'm running out of room. 8 times, I like 8 times 6, yeah, 54 times 1. And oops, let me expand that out. So if you erase that, what you'll get is 2 equals, let's expand it out, 8 minus negative 8 times 6 minus 54, and you get 8 times 7 minus 54 equals 2. Wow, so from here you get, okay, x is negative 1. X equals negative 1, and y equals 7. That's the solution. It's not the only solution, and that's not the only solution. So let's do it with, normally it's with bigger numbers. I'm giving smaller numbers to be nice. Let's do 15 and 20. You guys want to try it out with 15 and 20? Okay. Oh, wait. So what you're trying to figure out is like 15x plus 20y. What is that going to equal 5? What are x and y? Oh, wait. That is such an easy example. It's okay. And that's basically how you solve a Diophantine equation. That's how you figure to solve them. Sometimes they're like, what is it? When is this equal to, like, when it's like 10? Then you just multiply what you got for this by 2. 15 multiplied by 3. Sometimes it gives you like 7, and then you immediately know, oh, that's impossible by Bézut's lemma. Okay, I'm gonna just rush through this then. Okay. So let's start off with 20 equals 15 is 1 plus 5. And then we kind of just stop there. Equals 5 times 3 plus 0. So 5 is the last one. Literally, we start from the second to last one. So it would be just this equals 5. And then we would just end there because we have our original numbers. This is actually a really hard concept. A lot of high schoolers don't know this. This is a way to solve Diophantine equation. How do you figure out all the sums? Do you guys know what a parametric is? The parametric equations. This parametric equations. What we're gonna do? We have a lot. It's okay. The rest is all. Yes, it is the one with t. So parametric equation is like x equals 5t, y equals 3t. Why would you need to know this? Because it's used in science a lot. So like in physics, physics and calculus, you will use parametric. In like algebra, you don't really need to use it, so a lot of teachers don't teach it. But it's used a lot in other areas. So we're adding in another variable and we're putting like x and y in terms of it. By the way, if you're freaking out right now, this doesn't appear very often in AMC. If anything, it's going to appear like the question I showed you earlier, which is like Bayes' lemma. But if it might appear, see, I don't know anymore because AMC has gotten so much harder over the years. So this is like a little bit. Okay, so parametric equation is, actually, I'm not gonna scare you guys with that. So we're actually gonna, let's just go to Chinese remainder theorem. Have any of you guys heard of Chinese remainder theorem? What is the Chinese remainder theorem? Yes, so someone asked, okay, wouldn't all multiples of 5 work? Yes, they all work. As long as you can just solve them all using that way. But anything that's not a multiple of 5 would not work. That's what AMC will probably ask you. It might ask you to solve for one, but you will notice that it's not divisible by the greatest common divisor, so there's no solution. So Chinese remainder theorem is, yes, of course. I will share the handout. This is the handout. So I'm like, I will do it after the session because all the practice questions are on it. And I may or may not have forgotten to split it. So look at how hard the questions are. So Chinese remainder theorem is actually doesn't tell you much. I mean, it does. It's using like any number theory question that's going to appear on AMC is going to probably use it, unless if it's like a digits question. So Chinese remainder theorem states that, let's say you have like 4 mod 5 and 3 mod. Okay, x is equivalent to, right? It's like a systems of equations question. So if you're trying to solve for this, basically what Chinese remainder theorem tells you is that there's going to be one solution. It doesn't tell you what the solution is, but it tells you there's going to be one solution, mod 35, which is 5 times 7. But this only works if like these two are relatively prime. So that basically says that 5 and 7 aren't divisible by any number greater than 1. Any positive integer, be more specific. So they have to be co-prime. Is that answer 24? Oh yeah, it is. It is 24, but Chinese remainder theorem doesn't tell you that. It just tells you there's one solution. That's all it says. And you can use it in reverse. So if something gives you like x is equivalent to 2 mod 35, that also translates to it's equivalent to 2 mod 5. Well, I don't think this is Chinese remainder, but kind of. And 2 mod 7. So kind of the reverse works too. It just tells you there's one solution. That's all it says. If it's coprime. So like 4 and 7 also work, but 4 and 6 does not work. Oh, one solution mod 35 though. There's only one solution mod 35. Multiple, well, basically I'm saying it in like the range V35. You're trying to be like mathematically like correct. But basically that's all you need to know for a competition. Do you guys want to do a practice problem? Oops. So this is what it is. There's one solution when you multiply it by the product. So basically, that just states that there's one solution for this. Chinese remainder theorem, it doesn't tell you how to solve this. It just tells you that there's one solution. So you guys want to solve it. And why is it useful? So people don't try to solve for like 5 solutions in mod 99. There's only one. And it's really helpful when the numbers are bigger, but that's basically what it says. And it's used in so many questions in AMC. Okay. Now, how do you solve for these equations like quickly? Guess and check. Their AMC is not going to give you a huge number to where you need to actually solve for it, but they're just going to give you like 9 and 11. They're going to give you, most of the time it's going to be 4 and 25 for like mod 100. Like, what is the last 2 digits of this huge thing? And it's going to be mod 4 and 25. That's what Chinese remainder theorem. Right. And here's the second question, if you guys have solved it already. And Chinese remainder theorem says that you can split this into mod 3 and mod 4. I don't know if it's Chinese remainder theorem, but you can split it into mod 3 and mod 4 in x squared. Woo! Okay, so it's almost 5:30 and I need to give you guys, yeah, so you would get 60 for the first one. The second one, I'm just going to show you guys the answer. So the solution is, by Chinese remainder thing, we can split it into mod 3, mod 4. We pick 3 and 4 instead of 6 and 2 because 6 and 2, they share a common divisor of 2. Can I explain the first example? It's guess and check. Guess and check it. Chinese remainder theorem says there's one solution. It doesn't tell you the solution. So you would have to guess and check. So I would go like, okay, 6 doesn't work. 15 doesn't work. 21, oh wait, 24. 24 works. And yes, yeah, that's Chinese. Like a lot of people think like they look at the theorem and they think it's like so hard, but it really just says there's one solution. That's all it says. You can search it up. It's really intuitive in my opinion. The second yes has no solution. Someone got it. It has 0 solution. So Chinese remainder theorem, we can split this up. This is the most, so with like 100, not 100, I already gave you that. Like, sometimes you normally have to split it by prime numbers. So prime numbers, so 3 and 2 squared. You can't do 6 and 2, you can't do 1 and 12. For 100, you would have to do it 4 and 25. You can't do it like 2 and 50, because then Chinese remainder theorem doesn't apply. That makes sense. So 4 and 25. If you guys did 33, what 2 numbers would you have to split it by? For 33. You can move. It would be, it would be 3 and 11, because 33, you can't do any other, 33 can't do any other number. But they have to be relatively prime, so they can't share any divisors. But they also have to multiply to 12. So 4 times 3 is 12. 11 times 9 is 9. There's no solutions because there's no solutions to this equation. If you test it out, if you know your squares, quadratic residues, x squared can never be 3 mod 4. You can test it out. This is weird. Okay, so I will give you guys this practice question later. This is also a practice question. Okay, so there's Fermat's little theorem that Timothy's gonna talk through.
Okay, so for Maslow's theorem. So these next like few topics are just going to be theorems that you should know and try to remember. So okay, so let's start off with Fermat's theorem. So this theorem is basically Euler's totient function, for more specific. So we're going to talk about Euler's totient function later. But okay, so we'll start with Fermat's theorem. So in this equation, right, you see a to the p minus 1 is congruent to 1 mod p. So p is always a prime number, and a is going to be any positive integer that is relatively prime to p, right? So you this yeah, you kind of need to know this theorem. This theorem comes up this one, yeah, it does appear a few times usually, like maybe like once or twice during AME, I'm not sure, but you should still know this. It's pretty important. Okay, next, the next theorem. Okay, do you want to scroll? Do we want to do the practice problem first, or
Oh, because we can just give that during practice.
yeah, we'll do that later. Okay. Second one. Okay, so now we're going to talk about Euler's totient function. Okay, don't get scared by that big scary thing that's down there. Anyways, this theorem uses the totient function. So the totient function calculates how many numbers under a specific number are relatively prime to that number. It's very badly worded by me. Anyways, okay. So the pi, right? That's the multiplication of all. So p of 1 to p of n are all the prime factors of the number a. So Kara, can you give an example of like how to do phi function? Because I don't have the tools.
Yeah, okay. Phi function. How does phi function? What is phi function? Yeah, it is phi is a Greek letter and it looks like this. So if you ever see this, it's like this. That's how I write it. I think that's like written like more like this. But phi function tells you how many number integers less than, let's say 5. Do 1 and 5 share a prime any divisor? No, it doesn't. The greatest common divisor is 1. Greatest common divisors with 2 is also 1. With 3 it's also 1. With 4 is also 1. So all these are relatively prime or relatively prime. So what phi function would tell you is that phi of 5 would be 4 because there's 4 numbers, integers, positive integers, less than 5 that are relatively prime with it. So their greatest common divisor with 5 is 1. Let's do it with 6. 6 would be, okay, is 1 relatively prime? Yes. 2, greatest common divisor with 1 and 6 is 1. 2 and 6 is 2, so it's not 1. 3 and 6 is also not 1. 4 and 6 is not 1. 5 and 6 is 1, and then 6 and 6 is not 1. So 1 and 5 is, that gives you 2 numbers, 2 integers. So that would be 2. Now, the creepy function he wrote there is how a faster way to calculate this. Because what if they gave you like 34 and you don't want to go through 1 to 33 trying to test out what is not to share any divisors? So you would do, what you would do. Oh, do you guys want to practice with like a small number first, like 8? What would be the phi function of 8? By the way, we're giving you guys a lot of concepts because like number theory is really broad. The introduction and number theory book actually doesn't go through most of this stuff. It's like intro. So the answer to this question is 4 because you can test it out and you see that 1, 3, 5, 7. Oh, okay. 1, 3, 5, and 7 are relatively prime. So what the notation gives is a faster way to solve this is so 8. Let's do it with 8 again. So you factor 8, you get 2 cubed. Another way of writing is basically you would go 8 times 1 minus 1/2. If you guys want to like think of it like logically, why does this work? Because if you think about it, out of all the first 8 integers, half of them are going to be divisible by 2. It doesn't matter what power 2 is, like 2 to the power of 3, it doesn't matter. It matters that it's divisible by 2. So it would be 4. So with like, let's do 24. With 24, it's a little bigger. It's 2 cubed times 3. So it would be 24 times 1 minus 1/2, and then 1 minus 1/3, and that's it. It doesn't matter that 2 is cubed. So then you would do 24 times 1/2 times 2/3, which is equal to 8. So there's 8 integers. And I think that's it. So
Okay, thank you, Carol, for the amazing phi function explanation, right? So, okay, I'm going to explain more into depth what this thing is. So basically, like the pi is meant to represent like all the primes, right? So x equals p1, right? So it's 1 minus 1 over of the first prime. Then you do that times 1 minus 1 over the second prime, and that, and then you multiply all of that by the integer itself, and you'll get phi of n. Okay, now we're going to move on to the real function, right? So p of 1, okay, so yeah, p of 1 to p of n are all the prime factors of a number. Okay, so now that you know the Tosha function, here is Euler's Tosha function. So this, it's actually not Tosha function, it's phi function. I don't know what I was writing. So here we have a to the phi of b is congruent to 1 mod b. So if you look at the Fermat's I think Little theorem, right? It's a to the p minus 1 is congruent to 1 mod p. And think about it, the phi function of a prime p, right, is always just p minus 1, because a prime factor has there's p minus 1 numbers under that prime, and they're all relatively prime to the prime. So it's just going to be a to the p minus 1 congruent, which is congruent to 1 mod p. And yeah, so to be honest, I don't really memorize the Fermat's theorem, because Euler's Tosha function kind of is the same thing, but yeah. So here, yeah, you're given it's a to the phi of b, which is congruent to 1 mod b, and this formula only applies when a and b. I didn't write a. When a and b are relatively prime. Now we're going to move on to Wilson's theorem. This is also just another random formula you need to know. So we need to assume that p is prime, and the formula is p minus 1 factorial is congruent to -1 mod p. That's kind of I think that's it for all the extra formulas you should know for AMC 10 to AME, and I don't think we have anything else, right, Carol?
Okay, so actually Wilson's you won't even normally need. Normally it's Euler's. Euler's Tosha is the one formula you actually have to know. So Fermat's is literally just a more specific, like Euler's Tosha, it's literally the same thing as Fermat's, except Fermat's is only with primes. This, if you plug in that b is a prime, it would also give the same. Okay, so we can finally do the practice questions, and I will send you guys this link, and hopefully guys, oh, well, you guys won't suffer too bad. No, this is math. So I'm gonna give you guys it really quickly. Let me see if I can drag it to the chat. And it should be showing up. If you can't see it, then how unfortunate. Oh, and I will break you guys out into different rooms. Let's see if I can do that. please DM me your grade level because we're gonna split you guys up into grades. Yes, the remainder of the class is practice. If you guys have any questions, you can also ask me. DM me your grade level. DM me your grade level. Tell me your grade level. Great, great, great. And you guys will work in your grade. Oh, there's something. Okay. Yeah. Grades. Put into your grades. Please. Okay, I think there's 30 so far. Wait, oops, I actually moved you to. Let me move. Okay, wait, shoot, I messed up. Let's see, it might take me a little bit to try and figure out how to. Okay, so room 1, we're gonna have 8th grade. And me and Timothy would just be in there. So tell me your grade level. Because I've only gotten like 4. Everyone else, I'm gonna be guessing what grade you're in. Okay. Okay, wait. Who is not in? Okay. Okay, wait. Who is in? Who hasn't told me their grade? Raymond. I think he's.